Hello, good morning, welcome. My name is Dan. This is Coding Rainbow. I believe that I'm streaming live now to 3 outputs. I'm going to check those in a second, but I just want to mention for those of you who might be watching this at some point in the future as an archived video on YouTube, check this video's description. It will have links to the various time codes where certain things happen, because now, at least for the first 5 or 10 minutes, is just going to be me getting set up, introducing myself, and checking to make sure everything's working and seeing what questions there are. So I'm going to do that right now. I'm first going to check and look at my YouTube preview. I see that I'm live on YouTube. That's good. So first of all, those of you who are watching live, please let me know. YouTube chat is the place that I will check most often. Let me know if the audio quality is okay, if you can kind of see everything, picture quality, etc. I'll show you the whiteboard in a second to check the focus on that. I'm going to now check Twitch. I think maybe I am streaming live to Twitch. Looks like Twitch is actually working today. It wasn't working last week when I did a live stream. And then the third place that I am attempting to stream to 3 outputs all at once, making good use of this internet connection here, is to Facebook. So I'm going to check, and I should be streaming to the Facebook Coding Rainbow page. Doesn't look like it is. Hold on, I don't want to waste too much time on this. But I'm going to just check and see and look at my page over here. I don't see it going anywhere, but you know what? Facebook schmacebook is what I have to say. If anybody is seeing this or got a notification on Facebook, please let me know. I'm just going to check my output settings one last time. It claims to be going there, but I'm just not going to worry about it. Okay, I'm going to hit record to record now I am also recording this entire live stream to disk as an archived backup. And I want to talk a little bit about what's going to be happening in today's topic. So let me go back and get the YouTube chat here. I am live on Facebook apparently. Okay. Okay, hold on. Mathieu, who is helping me with organizing the YouTube channel and editing, has reminded me of a very important point that I forgot. I've got to check, so I'm stopping the record to disk. And I'm going to check my output settings. The stream quality might be reduced for a moment. I'm going to go to record to disk, and I'm going to check settings. Hold on, everyone. This is just going to take me a moment. View details, frames per second should be fixed. Strict constant bitrate, keyframe aligned. All right, let me see. Very fast encoding default. All right, this should frames per second 30. Let's try that. Let's see if that fixes it. Profile main, keyframe, okay. All right. So I'm going to see if this fixes it. If not, I will have to investigate that more later. So now I'm recording to the disk again. Okay, looking at the chat. Yeah, forget about Facebook. You know, the only reason, I don't know what the only, okay, so I'm streaming. The place that you should be watching this if you want to interact live is YouTube. YouTube/Schiffman/live. But you can the quality might be better. You might have a preferred platform, and then you could just watch it and enjoy it. So let me say a few words about myself and the topics that I'll be addressing today in this particular live stream. So my name is Dan. Last name is Schiffman. I have started this thing, which is a live internet show, lesson, tutorial, something that I'm doing once or twice per week. And I am demonstrating a variety of different programming concepts and techniques, covering topics from JavaScript to Java, JavaScript using P5.js, Java using something called processing. I'm covering other things like Node. I'm looking at computer vision with the Kinect. I'm looking at other kinds of tools like Git and GitHub. So just a variety of topics by request through different means. And what I'm doing is I'm doing these live streams, and that's what's happening right now. Today's will go for somewhere between 1.5 to 2 hours. Definitely last time it was almost 4 hours. That's absolutely not going to happen today. And I have 3 topics that I intend to cover today. The first being a continuation of fractal trees. I'm going to do a tree in 3 dimensions in processing. I'll show that to you. The other thing I want to look at has been requested several times is how to use GitHub Pages to host a website. And the third topic is I want to look at something called the Superformula. So this is what I'll do live. After this live session ends, various pieces of it, this hour and a half to 2 hours, will be edited down into probably 3 short 10 to 20 minute video tutorials, and those will be uploaded and archived on YouTube. So you can enjoy this live. If you're watching this in the archive, you can look in the description of this video where there will be links to various time codes, or you can wait for those edited videos to come, which usually come online on YouTube within a day or two. Let me mention something else, which has briefly been asked about. So I now have something called Patreon, patreon.com/codingrainbow. I'll show you this URL. That's the URL. You can go to patreon.com/codingrainbow. This is 100% optional. What I'm using this Patreon as a means for helping to fund this channel. So I want to just talk about this for a second. So, I work full-time at New York University as a teacher. My job at New York University, I teach at a program called ITP, and I am paid to teach classes. I am paid to do research, and really my research in my mind is educational initiatives like this YouTube channel, working on open source software like P5JS or processing, administering other types of community initiatives that the Processing Foundation does. Those are the kinds of things I work on in addition to my teaching. I'm also required to do service to the university, which means things like help plan a student show or serve on different committees and that sort of thing. So one thing that people who work at universities often do is they publish textbooks. And those textbooks are sold. And sometimes you'll get paid a royalty for a textbook that's sold. So you can do that with the publishing company. I have, for example, I'm going to totally just ramble about this for a little bit. You can skip ahead if you're watching this in the archive. So I have a book that I've published called Nature of Code. One of the things that I'm interested in doing as part of my research and kind of practice is looking at new models for open source publishing. So I don't necessarily mean free. I mean free as in open, but with a paid option. So I have done this now with something called Nature of Code. This is a book that you can read entirely online for free. I will go to chapter number 2. Here is all of chapter number 2 here. I could make it bigger so you could see it if you want. So the entire book is available online for free. You can also buy a print book, or you can, if you want, on the homepage of this website, also get the PDF for whatever price you choose, whether that be $0, or whatever. So this is something that I experimented with a couple years ago, and it was successful in my mind for what I wanted to do. I get lots of people who email me and say, oh my goodness, I would have never been able to, I'm a student and I can't, spend money on this, but I'm able to look at your book. Thank you so much. And then I also get people being like, I'm so glad you did this, and here's $10. So it is a second source of income for me, and it's also a nice thing, I think, to have open in the community. So to me, one of the things, I have this other book called Learning Processing, which was done with a traditional publisher, and if you could just find the PDF for free online anywhere through pirated means. So I feel like if it's going to be available that way, why not just make it available for free, and people can pay if they want to, or not pay, but it's out there. So that's what I did with book publishing. That was my experiment there. So now, a few years ago, I started making videos for my courses that I teach at NYU. And so I just was doing that as a supplement for the students. I would also put them online so other people could watch. I was doing that on Vimeo for a long time, telling a story. This is me telling, I'm going to be done with this story soon, but I want to give some background here. So I should have slides to show you. This is a stream of consciousness, not a prepared presentation. So I, over just last summer, even though I've been making these videos for 3 or 4 years, just over last summer, which is summer of 2015, almost a year ago, I started putting these videos on YouTube. And I noticed a new audience appearing on YouTube. If I look at my analytics, there's a lot more of an international audience discovering the videos, just more people in general. So I thought, okay, so I want to keep these videos online and for free. But is there also a revenue stream involved? What if someday I decide to quit working at NYU? Could I be a full-time person who sits in my fantasy, my cabin in the woods with a recording studio, just making videos and talking to people on the internet? So what are some, I'm lucky enough that I can kind of have the flexibility to do this, whether it makes money or not, because it's supported as part of my quote-unquote research. But I think that what if what, as an experiment, and also possibly like maybe this is something that I do want to do, what are some ways of funding this? So I have experimented with YouTube ads. Currently, the amount of views that my channel gets, the income from those ads is about between $100 and $200 per month. That's what it is. So another thing that I am now experimenting with, which is totally optional, is this thing called Patreon. So what Patreon is it's sort of an optional subscription service. You pay a monthly fee to support this channel. And you know, it's like a Kickstarter, it's supposed to come with some set of rewards. So what I don't want to get into the business of is there are private videos that only the Patreon subscribers can see. So I want all of the content to always be open. So what you can, if you're interested in what I have done, is that I have, and this is what I have so far through feedback and discussion made as the particular reward. So what makes sense to me is for subscribers is to have maybe a forum where people can ask questions and discuss topics related to things that are in my channel. So I'm using something called Slack, which honestly I had never used before a week ago when I set this up, and seems to be fairly successful. I'm also, I'm always taking suggestions and questions from the audience, and I will continue to do so. But I am going to, use that as a particular forum to pull questions and topics out for the videos. And the other thing that some people have requested is having offline access to the video files. So I haven't done the best job of organizing this, so I'm going to attempt to do a better job, but I currently have a Google Drive folder with MP4 files of every video I've ever made, and I'm sharing that link with people who subscribe to the Patreon. So this is something I'm doing, and you can see that currently this is now at $165 per month. So in total, the channel right now is between $300 and $400 per month. I do have expenses associated with doing this. I have purchased lighting equipment. I have purchased computing equipment. I have hired, I mentioned Mathieu, who is helping me with organizing the channel and editing videos. One thing I really want to do is close caption every single video, and I'm just going to use a paid service to do that. So as soon as I reach a certain level of funding, I'll start using that money to do that. And I'm cycling the cameras now, and I expect that as time goes on and I have more ideas and maybe want to get more of a, this might be the permanent space. I want to speak a little bit about that in a second. But so all these things, I'm just kind of giving this a try. So your feedback is encouraged and welcome. That's my spiel. And I'm going to end the spiel. If you have any questions about that, funding, Patreon, open source publishing, video making, all that sort of stuff, please ask them in the chat and I will answer those questions. Otherwise, I'm going to start getting to today's actual topics. Sound good? I hope it sounds good to you. Okay. I don't have any coffee or tea today. It's much too hot. I have some water. I do have a fan going already. And I'm going to close down the Patreon. Okay. Close down these links. So let me speak. How do you... Somebody in the chat will help answer how you spell spiel. I don't know how to spell spiel. All I know is I'm a little mashugana. Okay, somebody can figure out how to spell that. Okay, so let me first get to my first topic of today. I didn't even actually, so let me go to my YouTube channel for a second. I have a new playlist called Algorithmic Botany. And this playlist currently has 3 video tutorials on it. One is just basic recursive algorithm to draw a fractal tree. Another is using the same algorithm to draw that tree again, but keeping all of the branches and leaves of that tree in objects so as to be able to sort of imbue that tree with physics and animation. That's video number 2. The third one is using a particular algorithm called an L system to generate the tree. So I'm not going to go into those right now because those 3 video tutorials exist. I did them in last week's live stream. And there's a 4th one that I haven't yet turned on into this playlist. It's ready. It's sitting in my channel on private. Right after I finish this session, I'll turn it to public. But it is called, it's an algorithm called Space Colonization. So I want to show you where this algorithm comes from. And actually, I think maybe I'm just going to go to this particular video's description. Hold on a second. I'm going to get to this link. This is Let's see if this will work. There we go. So there is a paper called Modeling Trees with a Space Colonization Algorithm. I just love that name because I'm like, today's topic will be 3D space colonization. It sounds like, wouldn't it be amazing if this YouTube channel could somehow colonize space? I mean, someday it will, because the aliens will come and take over and they'll all be watching my videos on the planet Zorg, typing on their Zorgbot computers or whatever. But for now, space colonization doesn't actually refer to outer space colonization. It refers to, in a way, you can think of the screen, your canvas, as a two-dimensional space or a three-dimensional space, and this sort of tree growing up and colonizing it. So I want to, what I want to do is, let me get the example. So I did this particular algorithm in, I'm just checking the chat. I'm trusting you guys that if anything goes wrong with audio, video, sound goes wonky, the screen starts going crazy, if you're in the chat on YouTube, please type something because I'm able to see it. Yeah, volume colonization is, I think, is a good way, is a term that's relevant for 3D. So what I want to do first is let me just open up this particular processing example. And I think, I haven't looked at this since last week, so hopefully this is going to, okay. So what this is doing here, and I'm going to minimize this. Oops, I've got some stuff running. Hold on a second here. Let me just, I don't want this running in the background. Although it will, if I watch my YouTube video while I'm making a YouTube video, it will increase my views and watch time. It could be very exciting. Okay, so what I want to do, excuse me for getting lost in my own thoughts for a second. Let me run this for a second. So you can see what's happening here loosely. So the way that space colonization works is you fill a space, right now in 2 dimensions, with points. And then you start from somewhere. It could be from the bottom, from the center, from outside of it. And you start to use all of those points as attraction points. So you have this kind of single branch moving, and it's kind of attracted to any of those points that it's close to. And as there are more points, it will branch off. Okay. But here's the thing. This is what I always get confused. Because the way that this looks, it looks like the way that we're solving this. It looks so much like the way that we're solving this is we have this thing moving from the bottom and being attracted to all these points. That's the visual result. But the actual algorithm works in the reverse. What I'm actually doing is iterating over all of those points and saying, are any of these points near to an existing segment? And if they are, pull another segment towards me. So in that sense, there could be multiple segments start getting added. We just start with a single segment at the bottom, and then a bunch of points to pull a new segment, and a bunch of points over here, pull another new segment. Let me try to draw this a little bit over here, and you guys tell me if this makes sense. So in other words, I'm just going to make a very simple demonstration of it like this. So let's say there's only 4 points, and what I do is I start with a single segment. So this is the first segment. So essentially what I do is I iterate over every single leaf, every single one of these seed points in a way. And I say, okay, here's a seed point. Is it in between some minimum distance and some maximum distance? Minimum and maximum. Is it in between some minimum and maximum distance? If it is, pull a segment out close to it. And then this one, is it between some minimum and some maximum? If it is, pull a segment out close to it. Now, the next iteration, this is now no longer, this is now within, hold on, I'm like, this is so hard. So hold on, because it makes sense to me in my head, but you draw these diagrams over and over again, sometimes I get a little confused. So let's just do it for a second here. Let's do it with 1 point for a second. Here is the segment, and here is the leaf. I want to draw the leaf as an open circle, and the segment as with closed dots. So what I'm saying is, again, let me say that again. This is actually in between the minimum and maximum. So another segment would get pulled towards it. Now, Now, the next iteration, I look for, is it between the minimum and the maximum? It is not. So it does no, so this ends right here. So if this were the only leaf, it would end. But you know, if there were another leaf here, then suddenly this one might be in between that, and then this would get pulled this way. So these branches start getting just pulled around, segments get pulled around, and once they get close to a given leaf, that leaf is kind of done and gets deleted from the system. And obviously this is just with like a couple, but if there are all sorts of things everywhere, things start like branching around, you know, like this. Okay, so this is the idea. I'm going to look at the chat to see if that, and so we could run this again, and you can kind of have a sense of maybe this is happening. Every iteration, so I see, I missed the whole, I missed maybe everything in the chat. Oliver Wright, I just noticed, is writing a comment. I don't think that happens in one iteration. So let me explain to you what happens every single iteration. Every single iteration, for each leaf, every single branch is checked. If the leaf finds a branch that it is too close to, it's done. And when I say branch and segment, I'm using those words interchangeably. Branches are segments that are growing. If the leaf is close to a given branch, then a new segment is added pulling towards it. But that new segment, hold on, let's see what here's the tricky thing. That new segment could also be close to other leaves, and those forces that are pulling get averaged together for what that segment actually does. So we can see that happening here. Boy, this is like one of the hard. This, by the way, I had like nightmares between last week and this week about like how confusing I was in this. I mean, that's why I haven't. That video, this space colonization video, is 45 minutes long. The one where I build this from scratch. So let me just show this to you. So this is where I'm looking in processing. This is me looking at every single leaf. So for every single leaf, I need to find what branch is closest to it. And so I start looking at all the branches. If a particular branch is within that minimum distance, that leaf is done. So we're done, we get out of this loop. So a leaf can't act on other branches if it's already close to one. If that particular branch is really far, it's ignored. Otherwise, we try to find the closest one, and that closest branch then gets a force added to it from which it'll make another segment attached to it. Okay. Yeah, so I forgot. I did this last week at the end. Oliver in the chat, Oliver Wright was I want to just thank Oliver again in the YouTube chat, was extremely helpful last week when I tried to build this from scratch because I kept having bugs and getting things wrong, and he was typing in wonderful, helpful suggestions into the chat, which fixed things. So what I want to do, so that's the sort of, does anybody have any questions? I'm going to give you guys a minute here to think if you have any questions about this particular existing example. Because what I want to do is now take this example and move it into 3D. So I'm going to give, and I already did this last week, but I'm going to do it again. While I'm waiting to see if you have questions, I'm going to pull up that one and just see what it looks like. Right. So this is what I've got so far. Using PZCam. I'm trying to think if there is anything that I could do here to make the rendering a little bit nicer when I start to build it from scratch again. Oh yeah, a lot of people have asked. So I'm getting a bunch of questions in the chat, which I'll answer sort of briefly, randomly before I go into this tutorial. A lot of people have asked for a Mandelbrot set as a challenge. I absolutely would be happy to do that. I will check in the Slack group if people are interested in that, and sort of where I have a poll running. And then I'm also been asked if I'm planning new videos on genetic algorithms and artificial neural networks. I am planning, but I've kind of got this list of things to get to. My Cadenza course, which is an online course that's out and running that I did with a partner with a company called Cadenza, session 5 is all about genetic algorithms. So I'm going to wait for that to come out. And see how accessible that is to people. And if it's not, I might just redo some of those videos on YouTube. But yeah, please keep asking about that. Okay, Razor in the chat asked if I'm American. I am American. I live in New York City. I didn't mention, I'll just mention this now, that I am doing these videos from the School for Poetic Computation. If you're interested in learning about the School for Poetic Computation, please go to sfpc.io. This space is completely empty right now. There's nobody here but me, but starting tomorrow, they have a 10-week program with about 12 students learning and creating lots of amazing, interesting art projects. So there'll be lots of people in this space. So maybe I'll bring some people in to show their work or that type of thing as well. So that should be interesting. Oh yes, branch thickness. Okay, right. So let's, branches have a preference to go up. Yes, that would look good. So, on the one hand, I want to make this look better. On the other hand, I just want to get the sort of basic drop-dead version, simple version of the algorithm out there, and then people can actually put their own design ideas on it. But let me think about branch thickness for a second, because that should be pretty easy to do. The tree where I am drawing it gets these lines with a particular stroke. So it seems to me that the branches are being added over time, kind of from like bottom to top or from center to out. So, and they get appended to the array. So the later in there in the array, the less thick they should be. So this should be something I should be able to add, which I'll, the total branches is branches.size. And I should be able to do something like, say, the stroke weight equals map. I need to, so I'm using this enhanced loop, but let me do it this way. Let me do this. Branches.size, and then I'm going to say branch B equals branches.getI. So I'm just looping with I right now, because what I want to do is map I. So if you're at the beginning, you're very thick. So the I starts from 0 and goes to the length of this array list. And if you're at the beginning, maybe you have a stroke weight of 10. And if you're at the end, maybe you have a stroke weight of 1. Let's see how that works. Now, I don't know if the stroke weight really works in 3D. Let's try to make this much more extreme. I don't see this really working. Let me go to the 2D one for a second, just to see if this idea works. I think the thickness isn't just determined by how early it is. Oh, whoops, what did I do? Did I miss something? Oh my goodness, I didn't even add it in there. Ugh. I'm missing some really obvious things. Sorry, everybody. Thank you. I just made up the variable, didn't add it in. No wonder it didn't do anything. Yeah, it kind of did something. But you're right that, oh, well, see, the branches keep getting added and added. And also, by the way, using strokes in 3D is kind of not the best. You can see there's some sort of flaws in the rendering. All right, so how do I want to do this? I need to stretch. So Rec makes a suggestion. Instead of lines, what about stretched cylinders? 100% I should absolutely do that. I'm just being kind of lazy about it. And I didn't feel like, I have a secret to confess. I'm not really a 3D person. So I'm not really prepared for this 3D stuff. I know I could do it. I feel confident I could do it, but I don't want to spend all day figuring out elaborate 3D geometry. So I'm just kind of using stroke and stroke weight as a trick. And then what I would love is for people who would then take this example and do some more thoughtful 3D stuff with it. But I would really like to figure out this thickness thing. Let's go back to before I actually start the 3D tutorial. Let's go back to the 2D version. So I think just let me grab this for a second. Oops, here. And I'm just going to do this in 2D because it'll be much easier to see. And oops, and I think, oh, I forgot the if parent is null. So this is it happening, and you can see that. No, that seems about Right now, what's going to happen is they're just going to keep getting, no, that seemed to do the job. So I think my instincts were right. They are getting thicker over time because I must have forgotten, there must be something that I need to add to the code to stop adding branches over and over again at the end. So, so let's take a look at this. Right? Where is my core algorithm here? Let's print, in tree, there is this grow function. Let's print line branches dot size. I think I'm adding branches over and over again at the end. So you can see here right now, this is the total number of branches in my system. And we look at this growing. Right, let's look at these together. We should see, it should be done. And you know what's happening? I think some of these little flaws are causing there to be leaves that never get, they're like, these two leaves are on perfect equidistant sides of a branch, so they're like never get removed from the system. It continually grows the equidistant problem. We've got to solve that equidistant problem. Okay, let's look and think of where we could figure out to solve that. So where do I remove? The whole thing is that branches need to be removed. It can't possibly be as simple as this, right? I think it might be just like checking if it can't possibly be that simple, right? No, because that just is like making a smaller minimum distance. I could add small randomness to the direction. Ooh, that's a really good idea. Oliver is like my savior. So let's do that. What if we add, I love this idea. Okay, so where would be a good place to do that? So here is where, so I could just say something like p vector r is a random equals p vector dot random 2d. And then I could set the magnitude of that vector as something kind of small, like 0.01. So it's a tiny little thing. And then I could say closest dir dot add rand. Is just having a little bit of random direction going to fix that equidistant problem? Let's see. I think I still have it. Okay, so what if I make this kind of bigger? Now I think it's eating up everything for sure. Okay, there we go. So that fixed it. Interesting, just adding random direction. But did I lose the sort of purity of this fractaliness? I'm not sure. So this worked thickness-wise, which is nice to see. And so what if I say, like, what's the sort of like minimum amount? Let's try 0.2. Yeah, that looks like it's eating it up. Oh no, yeah, it gets it eventually. Yeah, so that worked. Let's see if I can do 0.1. I wonder if there's a time that I could target adding randomness more specifically. Oh, the normalization is broken now. But don't I normalize it again? Oh, I can just normalize it again. Or I can do this before I normalize it. Let's do that. I should do this before I normalize it, so the normalization doesn't get broken. Okay, so that didn't appear strong enough. There's still some places like where I have the equidistant problem like there. So let's make it a little bit stronger to see if that does it. Yeah, that seems to be doing it. I don't see any more. Yep, we can see it finished at 3,577. And you can see the thickness thing is working. So they're thicker at the bottom and less thick at the top. But this isn't really great, to be honest, because there's probably, like, these should probably match more. I don't know. Maybe it's reasonable. This all sort of depends on what exactly you're trying to do. But it's a one strategy. You could come up with other strategies. Add is still after normalize. Oh, thank you. Boy, I'm really, thank you. Let's see if this at 0.5 are still pretty good. Yeah. Let's make it a little. What if I give it like a completely random direction? That doesn't solve it as well. How do I make it much stronger? Well, that does it. Not so bad. It's not so bad to like add a kind of strong random force to it. It still has kind of a nice quality to it. Okay. Okay, so I think I'm far enough, and I'm going to start. There's 79 people watching here, which is great. I'm just going to check Twitch to see if there's anybody watching in Twitch. 10 people. Twitch definitely doesn't have as large an audience here as YouTube, and I'm just going to sort of check the Facebook thing. I'm going to. Okay, Facebook is working. Hold on, I'm just going to do something silly. Actually, never mind. Okay. All right. So sorry, everybody. I'm kind of okay. Okay. So let me recap where I am for people who are maybe joining late. So I have a YouTube. Whoops. I have a YouTube playlist called Algorithmic Botany, which has 3 videos currently in it. Recursive fractal tree, the same thing but with objects, and then L-system video. What I am going to add to it, which is this other algorithm called Space Colonization. So you can see what space colonization looks like here. So I'm going to. I already went through this particular piece of code. I'm going to do about a 10 or 15-minute tutorial on doing this now in 3 dimensions. Okay, so that's what I'm about to do, and I am going to. I'm getting the chat here so I can see it, and I'm going to get myself set up for that. So what I'm going to do here is, first of all, I'm going to undo. I want to get this back to what it was without the thickness thing. Let's see what I've got here. Okay, so that's without the thickness and with this sort of equidistant problem. And I'm going to save this. And I'm going to, this is this one. This is the 3D one. Okay, I'm going to close this. And this is the paper. I am going to have this paper as my image reference. It has, by the way, this is a nice diagram, I think, which helps illustrate what's going on that I would recommend, probably better than my kind of crummy diagrams. And then I'm going to here. So this is, so a thickness is probably discussed somewhere in this paper, and I did read this paper, that was last week, I don't remember it. But this is like the basic idea of what I'm trying to create. So I'm going to leave this open here as kind of my starting image. And then let me make, this is the 2D version of it. Oops. And in processing, I'm going to have this running. And you know what I'm going to do? Just going to have it start from the center. So hold on, I want to start the tree from the center. Okay, so I'm going to do it this way, just as a kind of a way of looking at it. Okay, so I think I am basically ready. Let me zoom in on this. And I'm going to cycle the cameras. I'm going to erase the whiteboard here. And hold on, I'm just about ready to start this particular segment. I'm looking for this. Just erasing the whiteboard over here. I didn't switch the camera view. Sorry about that. All right, how's everybody doing? Everybody feel good about this? Ready for this? I think this hopefully won't be famous last words that long. Oh, it's raining in Paris. It is hot and sunny in New York. This is not the best space to be when it's hot because I have these bright lights which generate heat. I've got a fan going, but there it is. Okay, here we go, everybody. I've got my, by the way, this is the Processing Classic t-shirt. This is the original first Processing t-shirt. I feel like we should make these again. I saw people have requested Coding Rainbow t-shirts and stickers, which somebody will remind me. I can try to make those available. Okay, let's see. Here's this pen. Here's my tree. And I am ready. Okay, here we go, everybody. I cycled the cameras, didn't I? Yeah. Raining in London, raining in Germany. I got a lot of European viewers today. That's great. What? It's like 7 in the evening, I guess. So this is a kind of good time. You're all at home. You're like, got your popcorn, watching me program, which is, you know, I'm very, very happy that you're here. Okay. Okay, here we go. Hello, this video is a follow-up on my previous space colonization video. Now, I wish I was talking about outer space colonization. I am not. I'm talking about an algorithm called Space Colonization, which is outlined in this PDF paper here that you can find a link to in this video's description. And it is possible with this algorithm to generate trees like this. So last week, time doesn't matter here, but in my previous video, I made a version of this algorithm. I actually did it in JavaScript using a JavaScript library called P5.js, but I have this same code running now in processing. And I switched over to processing because the point of this video is to extend this algorithm into 3D. So I want to take, and let me run it here for you. I want to take this idea, which is using this branching algorithm. Come on and run, please, code. Using this branching algorithm to take this from a 2D world to 3D. So let's talk about how this has to happen. So first, what's the basic idea for this? What's the basic idea behind this algorithm? So the idea of this algorithm is that you have a canvas, and you fill this canvas with points, and these points are known as leaves. So maybe you fill this canvas with a bunch of points, and then maybe you start at the bottom. And you create a branch segment, and you keep growing branch segments all the way up until you get close enough to some of these leaves. Then what the algorithm does is it says, okay, any leaf that's close to this particular branch segment, pull a force, have it become an attraction force. So maybe this one and this one are close, so a new segment is made. And then this one and this one and this one are close to this one, so a new segment is made here. But this one is also close to this one, so another new segment is made. So all of these leaf points become these points of attraction that start just pulling out these branches. And you can see that happen. I'm going to come back to the code, and I'm going to change here. I'm going to in setup. I'm going to say frame rate. I'm going to just say 5, so 5 frames per second, and we can watch this happen a bit more closely. So you can see here these branches are getting pulled and pulled towards all of these points. And as they get pulled towards these points, those leaves disappear. Now, there's a couple things I want to mention about this. I'm kind of recapping my previous video, but I think it's worth it before we move to 3D to make sure we understand all the pieces here. So number one, I just want to kind of recap. This particular program has a set of objects. It has a leaf object. That are these seed points here. It has a branch object. The branch object being these particular segments, all of these segments. And then it also has a tree object. And the tree object keeps track of an array of branch objects and an array of leaf objects. So the algorithm goes something like, for every leaf, see what branches are within a minimum and maximum distance and add a force to those branches, and then have all those branches grow a new branch off of them with the direction of that force. So the tree itself is iterating through all the leaves, then applying forces to all the branches, then making new branch segments. And as leaves are close enough to a given branch, they get deleted. So this leads me to an issue, though, that I feel like is worth resolving in this example before we move on. Look at this. There are some leaves that just won't go away. They're there. They're stuck there. I can find another one. Over here is another one. The reason why it's stuck there is that they're magically somehow exactly equidistant from a particular branch segment. So the force can never go towards one to get a little bit closer and then be removed from the system. So I don't know, I'm looking at you, internet, watching this video to come up with solutions for this problem. I had a wonderful solution suggested by Oliver in the chat recently, which is just to give each branch a little bit of extra random force to it, so that every once in a while as it's going there, it'll randomly turn. And in that case, it'll eventually find these branches, these leaves, and get removed. So let's add that here. And I'm going to go to the part of the algorithm where we add those particular forces. And actually, what I want to do, I'm going to do that in a different place than I did it before I was practicing this. So this is where those new branches get added. And this is where the branch's direction gets averaged based on how many forces were applied to it. So what I want to do right here, I'm just going to try making another random vector. And I'm going to say, I'm going to add that. So right before the vector is about to be, right before the new branch is about to be born, I'm just going to give it a little bit of random motion to it to see if it can, when it's getting stuck, if it can skew towards one of those leaves. So let's run this again. Oh, and I have the frame rate at 5, so let me cancel that out. Let's run this again. Come on, I don't know why my command R isn't working. Oh, I'm in debug mode, no wonder. So, oh, that's way too much. Look at that. That kind of ruined it. It did something, but it's kind of like crazy now. So I probably shouldn't have added it here. Okay, so let me go back here. Let's try to make that not so strong. Let's make it really, really weak. So I'm going to set its magnitude to something much, much weaker. And you can see maybe that wasn't strong enough. So it's still like I've got these equidistant spots there. So let's make it 0.1. That seemed to do the trick. There's a couple spots that are still stuck there. Let's try 0.5. It's a little less kind of like curvy and fractally, but it did work. So I'm going to just try 0.3. That looks pretty good. So I think I settled on 0.3 as kind of my number that I want to do. So you can see I at least have now resolved that problem. The reason why I wanted to resolve that problem is I'm going to add something. I don't want to be adding branches infinitely. And the other thing I want to do quickly to this before I move into 3D is show you, let's do something that's changed the thickness of these branches. So every branch right now has a stroke weight of 1. But what if branches that are made earlier at the center are thicker than ones that are at the edge? So a way that I can do that is right here. This is where I'm actually drawing a line for every single branch. So every single branch here is just a line between the the branch's position and its parent's position, connecting the one that's connected to it to itself. So one thing I'm going to do here is just change this loop to a regular loop using index I to branches.size. The reason why I want to do that is what I want to do now is I want to say each branch is going to have a stroke weight. So for example, if I say stroke weight 10, you can see all the branches are really thick. They have a thickness now of 10 pixels. But what if I were to create a variable and map its index? So the older branches are added at the beginning of the array. So its index goes between 0 and branches.size. And have that go, so the earlier ones have a thickness of 10, and the later ones at the end have a thickness of 1. And what if that is its branch thickness? You can now see we've got something here where the earlier they are at the beginning, the thicker they are, the more at the outside, the less thick they are. And I could like mess around with this mapping. I could just start with 5 or 6. I could actually go down to 0 to get them like much skinnier even at the end, which is kind of nice. So I think this looks kind of nice. And you can imagine how this might have, what kind of effect this might have depending on how you're seeding the points and where you're starting the root of the tree. Okay, so I somehow said this was a video all about 3D, and I probably spent 10 minutes here just getting ready for that. But we've recapped the algorithm, and we've also made it a little bit better by adding thickness here and solved a particular problem. And now we can actually do something that I believe will be quite simple in turning this into 3D. So let's think about this. So this is what's happening in a two-dimensional plane. I created in the canvas, I just created random leaf points anywhere. So what I want to do instead in 3D is I want to think of the canvas not as a flat plane, but as a sphere. So I'm going to create random points all inside a sphere, and then I'm going to have my first branch, the root of the tree, in the center of the sphere. Again, if you really want to create a tree, what you might do is create some kind of like ellipsoid in 3D, seed all the points, start the root at the bottom. But I'm just going to do something simple just to get this algorithm working, and then it's up to you to be creative to try to create a different set of seed points with a different starting branch. Okay, so let's come back over here and see if we can do this. Okay, so the first thing I need to do if I'm going to move into 3D is just add P3D. Oh, I'm not here. Is just add in size P3D. So what did I just do? I just added P3D. So I want to. So now it's rendering in 3D. I can actually just run this and see like, hey, same thing, but it's actually in 3D. Now, just so we can like get a sense of the camera a little bit better, I'm going to add a library called PZCam. So I've already installed this library. If you haven't installed this library, go to Add Library under Sketch Import Library. But I've already installed PZCam, so I'm just going to click Import. And all I need is this import statement at the top. Then I need to create a PZCam object. I'm going to say cam equals new PZCam. And I have to say this. So PZCam is this library that just automatically like makes this mouse interactive camera so you can spin around and zoom in and out of your scene in a very default way. And what I need to do, so I need to say this, referring to this sketch is where I want this camera to take over. And then I also need to give it a Z value, like how far away do I want to be looking at it. So I'm just going to say 100 for right now. And then I'm going to run this and sort of see what happens. So I can't seem to find, like, oh, there it is. So I'm off. One of the things that PZCam does for you is it makes 0, 0 the center of the window as opposed to the top left. So here in my tree where I'm creating the leaves, I actually want to create them. I want to create, well, first of all, I want to create the root at 0, 0. And then where I'm creating the leaves, I want to make the leaves not offset by the center of the window anymore. So let me just do that, and we should see now, there we go. Now, one thing is I'm kind of zoomed in, so I can zoom out and I can spin. But you can see now this is totally flat. This is kind of a nice effect just in and of itself. So I still have my two-dimensional space colonizer, but it's in 3D. And I want to look at it from further away. So let's make that 500. So you can see here. So this looks exactly like what we had before, but secretly it's in 3D now. So this is actually, I believe, going to be incredibly simple. All I need to do is, instead of making a two-dimensional plane of leaf points, right? Let's not call grow. So what do I have here? This system is just a whole lot of points in a two-dimensional plane. Why are they that? Because all I did was make random 2D vectors. So watch how simple this is going to be. Random 3D. I want to make, random 3D vectors, and I'm going to run it. And now you can see, whoa, okay, so what's going on? I made 3D vectors, but I only see two-dimensional points. Well, there's a bit of a problem here, which is that my points are ellipses. So what I want to draw, I need to draw those at their three-dimensional location. So I'm going to change this to translate pos.x, pos.y, pos.z. And now the ellipse can be at 0, 0. And I'm going to say push matrix, pop matrix, to make each ellipse its own thing. So I'm going to run this now. Oops, let me zoom back out. And you can see now I have this, let me zoom back in. I have this 3D sphere of points. Now they're ellipses, so as I turn to the side, they're no longer facing forward, and I can make them spheres. You know, there's any number of things I could do. Let's just make them spheres for a second, just for fun. What's more fun than making them spheres? I'm just curious to see how slow this runs. Now notice, look how slow this runs. So I don't want to make them spheres because I don't even need to see them for this algorithm to happen. But spheres require a ton of rendering because each sphere has like a zillion polygons. And I could reduce the detail in the spheres, and there's all sorts of things I could do. But I'm just going to leave them as ellipses. So I'm going to run this again, and you can see here, now I have this. So now all I should be able, I should just be able to grow the tree. I mean, all the math is going to be the same whether it's 3D vectors or 2D vectors. So let's grow the tree again. I'm going to turn grow on. And we're going to run it. And let's see what happens. If something is working, I can see all those branches happening. It didn't fit. But look, it's still flat. It's so sad. It's still flat. So why is it flat? Well, am I drawing the branches in 3D? I probably have a line function that's just doing 2D. So let me go back to the tree. All the way at the bottom, this is where I'm drawing each branch as a line between the branch's position and its parent's position. So I just need to add the z-coordinate for this line. And I got to scroll all the way to the right here to get also b.parent.pos.z. So now I should have a three-dimensional line. And let's see what happens. It's growing, it seems to be getting everywhere. And now, look at this, there we go. Look at this crazy three-dimensional, wacky, strange shape that I have. And I can zoom on into it and look inside and scroll around. And we can see there's different thicknesses. It's thinner on the outside. Now some leaves just didn't get reached. And it's hard for me to, I can't tell if I have this equidistant problem anymore. I don't think so. I think some leaves are just kind of too far away. So there's some ways around that. I could futz with this sort of minimum and maximum distance. Like let me make the maximum distance 200. And I think that's going to help things. So that I think that's probably going to, you can see now I got to everything. So that just by increasing that maximum distance, leaves that are kind of too far away will get found. Now, here's the thing. There's a bunch of things that I've done here. Yeah, it doesn't look, someone in the chat writes, it doesn't look like a tree. It doesn't look at all like a tree. So maybe before I go, I'll make this look a little bit more like a tree. But here's really your job. So your job is to be a designer. Come over here, please. So what have I done? All that I have done is create sort of a default view of the algorithm working. So, and think about it in 2 dimensions. I made a sphere. I filled the sphere with points, and I started in the middle, and stuff is growing out. So really, I almost made this like veiny, blood vessel-y like system. So if you want to make a tree, you've got to be more thoughtful. So on the one hand, I made a suggestion of what if you kind of create, and actually something like this might work well. What if this is all your seed points look like this? And then you actually start the root from the bottom. So you need to come up, what's your and if you read the Space Colonization paper, it will give you suggestions. What's the volume where you create all of your seed points? And then where do you start the root? So that's, on the one hand, going to make it look more like a tree. The other thing you need to think about is just, I just use three-dimensional lines, which aren't really, there's not a lot to them. So you might think about, well, actually, what you want to put are cylinders for each branch segment. And maybe you want to texture those cylinders with some kind of like wood-looking texture. And then you want to add some lighting to the scene. And then maybe you actually want to put, at the points that are at the end, you want to actually put actual leaves on like various parts of the branch. So I think there's a lot of kind of visual dressing that you can add. So there's your seed points, how those seed points are organized. There's where you start the root. Those things will get you sort of closer to the tree, as well as your sort of visual dressing. What's your lighting? What's your texturing? How are you drawing the branches? Are you adding like leaves attached to the branches? That sort of thing. So I would like all of you to explore those types of things. Okay, yeah, the other people are saying it looks like connections in a brain or a plasma ball thingy. Those are all excellent points. So let me at least get you started to show you where you can make these kinds of changes. So I'm going to save this as Space Colonizer 3D. All of the code will be uploaded on GitHub with a link. And I also, let's just add a few more things to this before we go. So what I'm going to do is say, let me make the scene that we're looking at a bit taller. So I'm going to make it 900 by 600. We can see, sorry, I want to make it 600 by 900. So I want to make it kind of, oops, oh my goodness. I hit something by accident here. So you can see I just want to have my window be a little bit taller. And then what I want to do is have the leaves start, I want the leaves to just go out by like, still be a sphere, but I want to offset them. So I want to say y minus equal like height divided by 2. So that should offset everything up. Yeah, there we go. So, so this is what I wanted to do. But then I also want, so that's way too much. And then I also want the tree's root. So in the tree object, the root gets a point. I want it to actually start at the bottom of the window, which is 0, height divided by 2. So I want to start the root at the bottom. So this is a bit more tree-like. So how successful this is, I'll let you be the judge of that. But you can see just by having kind of a tree at the just by having like a sphere of points up top and the root of and starting the root at the bottom, you get this kind of stalk root-like thing, and then it starts to branch out at the top. But again, maybe there's a uniform distribution of random points now, all in that sphere. Maybe there should be even more along the top and less on the bottom, or some type of like cone shape. I encourage you to experiment with it. But this, I think, will get you a little bit further into seeing it's kind of tree-like. And I'm addicted to spinning around this. Okay, so I think this concludes this video. I'm just going to, some people in the chat are asking, like, what did I do to change? So let me just mention again, since I did that kind of quickly. In the leaf object, this beginning function right here, this is where the initial leaf positions are set. Every position is a random 3D vector scaled according to the width of the window, which is about 300 pixels. And then I'm offsetting it by height divided by 4. So moving all the y positions up. That's where all the leaves are set. Now, where does the tree begin growing? The tree begins growing in the tree object, and the variable is this root branch. So the root branch, incidentally, has 2 arguments. The root branch gets where it's positioned, so 0, height divided by 2, so down at the bottom. And also that vector is the direction where it starts growing. So incidentally, if I were to change this to this, we'd have a problem, because nothing would happen. The tree is growing off to the right to infinity. So it needs to grow up, so to speak. There we go. Okay, so the process of it growing is really quite lovely and nice. And it'd also be interesting, like, all those branches are objects. What if you start moving the points after the fact, add some physics to it, have it blow in the wind? So many possibilities. Okay, so this was much longer than I had intended, but this is hopefully a nice follow-up to the previous space colonization in 2D video, and what I did here was fix a few things about it, add thickness, move it into 3D. I hope that you make something with this and that you share it with me. In particular, add your own kind of visual design spin to it, and I look forward to seeing what you make. Thanks for watching. Okay, live chat. That's the end of space colonization. Hopefully everything is still working okay. Let me see what time it is. It's 1:30, so I've been going about an hour. That was probably quite, I don't know if anyone was tracking how long that was, but I think I got up to like, I think I was doing that for like at least a half an hour. Okay. So I'm looking at the chat. Okay. All right. So here we are. So I'm going to save. Let me just save this and close this and close this. And let me now. So the other two things I had to do today are. I'm going to show you guys this. And I'm going to do this in P5. So this is just something called a superellipse. It's a simple algorithm to, instead of drawing like a set of points and make up a regular ellipse, you can make these kind of like crazy shapes. And then if you make the formula even crazier, I don't know where I put this. Is that this? Yeah, you can start to do weird, crazy stuff like this. So this has been requested. It was requested on the Slack that I have going with Patreon, and it was suggested, I think, also just on Twitter. So I'm thinking of doing this as a tutorial today, and then a lot of people have been asking for me to do GitHub Pages. And so let me go back to, I'm going to open up something else too, which is just, I've been doing a set of Git and GitHub tutorials. Where is that? Maybe under Documents? I had a to-do list. Old desktop. Oh boy. Other documents. Well, let me open up TextEdit. Probably has it in its open recent. Yeah, Git tutorial to do. So this here, this was my to-do list about Git and GitHub tutorials. So where I got to was number 6. Oh, and I did number 7. So I think having done all the way through number 7, I could actually do GitHub Pages now. So the two things I have left for today in the next hour would be GitHub Pages and GitHub Pages and the Superformula. Anybody in the chat? Anybody like dying for one of those? Let me know. And I'm going to sort of get myself organized here. I feel like I should do the GitHub Pages first. I kind of want to take a break from algorithms, especially algorithms that are hard. So let me get set up to do that. So let me get myself logged in on GitHub. I'm logged in as Coding Rainbow. And OK. I want to test something. So I'm just going to test this real quick. So let me try to make, so you guys can watch here. So I'm going to, the GitHub website does not comply with my desire for a larger font. I don't know if any of this is legible. Let me move this. I think I have this much space if I stand over here. And so that's pretty good. Can I make this one bigger? Yeah. So let me make a new repository, test GitHub Pages, testing GitHub Pages. So I need to make a branch. I'm just going to do this really quickly, and I'll talk through it when I do a tutorial. And then I need to go to settings. I just want to remember where everything is. Branches, make the default branch GitHub Pages, update, I understand. Go to here, and then go to branches. And then I want to delete master because I don't want it anymore, and then GitHub Pages, and then I'm going to create a new file. So I'm going to just create a file like test poem.txt. Let's see if it will do it, host a text file. This is my poem. And commit. And then if I go to settings, here, it should be here. And I should be able to say poem.txt. There we go. Yay, GitHub Pages. Okay, GitHub Pages works, even with just a text file. Okay, I'm looking at the chat here. I see a lot of people discussing. Because it's a... What about the rainbow is reversed? Is it the colors are in like the wrong order? Okay, so what I need to do here is wash my whiteboard. I'm going to do a GitHub Pages tutorial. By the way, so I'm going to do a basic, I'm going to do 2 videos. One I'm going to do with you don't even need to know HTML. I'm just going to put a text file in, and then I'm going to do another one. Actually, you know what? I'm going to do that one with HTML, a text file, and then with HTML also. And then I'm going to do, then I'm going to show you how to host your P5.js sketch with GitHub Pages. Okay, so I need to go back here, and I want to go to here. I want to delete this repository. How do I go to settings, and I go to the danger zone. We're in the danger zone, everybody. Delete this repository. Test GH pages. I understand the consequences. There we go. Okay, so let me come back here. Let me go to, how do I go to my repositories? Oh, I want to go to Rainbow Coder. Your profile. Okay. Okay, everybody, here we are. Let's see. Okay, how are we doing? We've got 80 people watching online, which is kind of amazing. I'm just going to check. Hold on, I just want to do something kind of silly. If you don't mind, if you will just, if you will humor me for a moment, I moved my Facebook live stream from my personal Daniel Schiffman page to the Coding Rainbow page. Oh, it's probably already over on Facebook because it only lets it. So I'm just going to quickly share it just so people know to switch over to there. So what do? I do share. Oh, no, this is all about algorithmic botany. No. Where do I find it? Oh, no, I'm in. OK, hold on. I'm just curious about this. So, oh, wait. I know where to go. Where? How do I see where I am live? Oh, there it is. It just says it just has the wrong description in it. That's fine. Yeah, so this is all from today, I think. Yeah, there I am. Okay, I see myself live. So I'm just going to share. Sorry about this, you guys. Whoops. Share. Sorry, everybody. Okay, and then I'm going to say public. Okay. Okay, sorry, I just thank you guys for humoring me there. I lost 4 viewers in doing that. Okay. Okay, All right, so here we go, everybody. I am ready to talk. One of my this might seem strange, but one of my favorite topics is GitHub Pages. GitHub Pages is awesome. In some ways, it's a little bit overkill. Like, what do you really need GitHub Pages for? Because you got to deal with all this Git stuff. But it's completely free web hosting. It's super fast, and it's great for all the collaboration stuff. So I think it's a really nice option. And so this video tutorial will be about using GitHub Pages. So let me just think about this for a second. So I want to make a list here. I'm going to try to recreate for a second that list of terms. Commit, repo, branch, push, pull. I haven't done merge yet, but I don't need to worry about that. What are some of the other terms? Init was one, but it's not really relevant for this. I think this is all we need for this particular. Okay, so I think I am good. Okay. Okay. Every in the chat writes, switch to Facebook. It is ahead of this video by a second. Okay. So Every's asking if I could do a 5-minute Q&A. I would like to, since I've just got the momentum here, do this GitHub Pages tutorial. And after that, I will take questions, if that's OK with you guys. Just because I want to just get moving here. So here we go. How's my, I like want to fix my hair, but I got it all cut off. And there is no fixing of it anymore. OK, here we go, everybody. Just got to kind of warm up a little bit here. We should do, everybody stand up and stretch. Do some like stretching. I don't know what I'm doing. Okay, this is going to be the tutorial about GitHub Pages. Let me get my button in place. The button really is not working for me. I got to work on the button. It's like I need some physical computing help. When the School for Poetic Computation students show up, somebody will come and help me with this, hopefully. Okay, here we go. Hello, welcome to part. I don't know what. Let me look at my. This was not the beginning of this video. I want to look at my GitHub playlist. I don't. Git and GitHub playlist. Okay, this is part 8. So this is the 8th. This will be the 8th video in this playlist. Okay. And I can close this. Okay. And also, let's get rid of the superformula for a second. Just not as much as open. Okay. And then, sorry, hold on. I do want to have terminal open. Sorry, everybody. I realize I'm going to want to use terminal briefly. And I'll just do desktop. Okay, in this video as well. Okay, now I'm ready. Okay. Part 8, right? Okay. Hello, welcome to part 8 of GitHub, Git, and all that stuff for poets. And in this particular video, I'm going to show you how to have your poem or whatever it is you're making web page hosted through GitHub. So your Git repository on GitHub can actually be, you can get free web hosting with it. So, and this is by using something called GitHub Pages. GitHub Pages is a rather large topic because there's tons of features that it has available for you, but I'm going to show you the very basics, just how to take your files and have them viewable through a URL. So that's the first thing that I'm going to do in this particular video. So if you've been following these videos along, there's these important Git concepts that I've been covering in each one of these videos. Commit, we have a repository. A commit is like a save. Branch is having a separate branch of changes that you might merge into your master branch later if you like those changes. There's push and pull, of pushing being to send and pull being to retrieve. So there's all this stuff that I've covered in all of these other videos. And the exciting thing is that using GitHub Pages, all of this stuff works identically exactly the same way. So you can have a project that you are working on through Git, keeping track of its history, collaborating through Git. But if you flip a switch and it's on GitHub, you can actually view that project as a directory of, as if it's hosted on a website. So let me show you how this works. The key to it is the under branch. The key is that typically by default, your Git branch is called master. That's the sort of like fundamental core branch of your project where your like final things are. Your main poem, your main code, whatever it is, lives in the master branch. For GitHub Pages to work, you want to get rid of this idea of having a master branch. You still can have one, but for simplicity, you can just think of your master branch as being called gh-pages. So as long as the branch that you're working on is called gh-pages, there is automatically a secret URL by which you can access. Now, there's a lot more to this, but I'm avoiding saying that now, and I'll get to it later. So let's come back up, and let's just do this right now. It's actually going to be quite simple and easy. I'm on my profile page. I'm the Rainbow Coder, for lack of a better username. And I'm going to make a new repository, and I'm going to call this Poem Website. So this is my repository name, Poem Website. This is a ridiculously bad repository name, but it's fine. You can come up with something better. And this poem will be on the internet and really on the World Wide Web, I'm talking about. So that's my description. It's going to be public. I want to initialize it with a README so you can see what I'm doing. So I'm just making a new repository through the GitHub interface, just like I always have before. So I am going to hit Create Repository. There it is. Now I have this repository. So notice here that by default, the repository lives in the master branch. So in order for it to use GitHub Pages, all that I need to do is click here and make a new branch. So I'm going to type in GitHub-Pages, and I'm going to select Create Branch, GH-Pages. So now I have this branch, GH-Pages. Now, here's the thing. That master branch is still there. And in fact, if I were to go to this repository again, by default, it's going to put me onto the master branch. So to make things simpler, I want to make sure that gh-pages is the default branch. So where I do that, I need to go to Settings. So I'm going to click on Settings. And under Settings, I'm going to go over here to Branches. I'm going to click on Branches. And over here, notice here, this is where it says Default Branch. So I want to go to this Default Branch place, and I want to switch Default Branch, and I want to switch it to GH-Pages. And then I want to click Update. Now it's gonna say like, oh my goodness, changing your default branch can have unintended consequences. It can. And this is, we're living a little bit in the danger zone here. But what's the big deal? There's nothing in this repository yet. I'm just making a poem. I'm messing around. This is actually quite okay to do with a brand new repository. You're not affecting anything else that's happened in the history because there is no history so far. So I'm going to say understand, update the default branch. And now the default branch is GH-Pages. So if I go back to this poem website repository, you can see that I am now by default in the branch GH-Pages. Now there's a little bit, this is fine, and I could stop here, but I want to be I'm really serious about GitHub Pages. I'm all in on GitHub Pages. So I also want to go over here to branches, where this is the link where I could view what are all the branches associated with this repo. And I'm going to click here, and I'm going to see that the default branch is GH-Pages, but I still have this other branch master. So over here on the right-hand side, there's this little trash icon. I can click this and actually delete the master branch. And this is worth doing because I don't want to by accident ever work on the master branch in this particular case. So I'm going to delete this branch, and you can see it's gone. It's kind of X'd out, and all I have now is a GH-Pages branch. Okay, we did it. This repository is now a repository hosted through GitHub Pages. So I can go to Settings, by the way, and I can scroll down under GitHub Pages. You can see here, your site is published at this URL. So by definition, if you have a GH-Pages branch in your repository, the URL for that repository will be your username.github.io/the repository name, which in this case is Poem website. Now here's the thing. You absolutely can use a custom URL. So for example, I have several websites hosted through GitHub Pages. Natureofcode.com, for example, is hosted with GitHub Pages, but it isn't at schiffman.github.io/natureofcode. So there is a way to do that, and in another video, maybe I'll explore that as a topic. It's just a sort of configuration thing, but you get this sort of free URL that you can use. Now, let's go to that URL. And you can see here, it's going to say page not found. The reason is there are no files there. There's no files there for me to look at. I mean, maybe in the repository, there is a file called README. I might be able to look at that, but let's take a step further. Let's add a file. So I'm going to go here under Create New File, and I'm just going to name the file. Now, I'm just going to make a plain text file, and I'm going to call it poem.txt. And I'm going to I'm going to write some poetry. GitHub Pages. Oops, GitHug. Oh, I wrote that by accident, but I'm going to keep it. GitHug is a hug on the pages. Oh dear, this poem is terrible. Okay, so that's my poem. You can send me a pull request to improve it. And I'm going to do commit new file. And you can see that it's committing it directly to the GH Pages branch. And you can see there it is. So I can see it here in my GitHub repository, but now look at this. I can go to the URL, and I can put in there poem.txt. So I can access that particular file, and there you can see, there it is. I now have a web page with this particular poem on it. Now, that web page is a plain text file, so all it shows up as raw text. Those of you who have used the internet before or browsed the web have noticed that web pages have different fonts and images and animations. So to go further with this, to actually host a dynamic website through GitHub Pages, you need to actually have HTML files, perhaps also image files, perhaps also something called CSS files. I happen to have a whole set of tutorials about how to use HTML, CSS, and JavaScript to create different kinds of web pages that you could go and look at and then come back to this. But I'm at least going to just in one step, I'm going to make an HTML poem just here so that you can see a little bit more. So what I want to do now is I'm going to go back and I'm going to create another new file. And you know what? I'm going to call this file index.html. If you name a file index.html, then you don't actually have to type in that file name on the web. It will be the default file that's open whenever I go to rainbowcoder.github.io/poem website. So I'm going to call it that, and then I'm going to type some HTML into this file. I'm probably missing some things you're supposed to have in HTML, but HTML is all about having these tags, open HTML, close HTML, open body, close body, and in the body I can put something like H1, which means header 1, and I can say poem, and then I could say like H3 by Daniel Schiffman, and then I could say like P, which is for a paragraph, and I could say this, rainbow, you are my rainbow. And then I could put a period and close the paragraph. And you can see this is, you can check out my other tutorials to learn a lot more about HTML, but this is writing some markup, which is giving it some formatting. And I'm going to just add a little more formatting, like I'm going to add strong. So this is going to make that particular rainbow bold. And then I'm going to hit commit. I'm going to say making an HTML poem, and I'm going to commit that new file. And you can see now, what do I have in my repository? I now have index.html in addition to poem.txt. And if you remember, this is what poem.txt looks like. However, now if I go to the URL and I just get rid of that, right? And I want to go to just the core URL, rainbowcoder.github.io/ poem website, and I hit enter, you can see there's my poem and formatted. So I've now used a little bit of HTML, and it's freely available on the internet. This is a website. People can contribute to this website by making pull requests. You can make changes to it through the GitHub interface. You can clone that repository down to your computer the same way I showed you in other videos. You can make branches. You can make changes. Just remember, the one thing that's going to be different, I'm actually going to, let's do this really quickly. Let's say you want to work with this locally. I want to get, I'm going to go to clone or download. I'm going to copy this URL, and I'm going to go to terminal. This is something that I did in a previous tutorial if you need to go back and look at that. And I'm going to say, first of all, just so you know, I'm on the desktop of my computer, and I'm going to say git clone. So we can see now that here is that, you can see there are the files. One thing for you to remember, if I say notice it's telling me I am on branch gh.pages. So if I ever want to get updated changes, git pull, normally we were saying things like git pull origin master. No longer is there a master branch. So I have to remember, if I use any of these other git commands, to always use gh.pages. Okay, so there you go. That's the basics of it. You can put image files, anything that you can do in a web page, you can put into this repository. You can add stuff, you can commit stuff. Your whole web page is there online for anyone to see and for you to work with through the Git platform. What I'm going to do in the next video, for those of you who might have come to this series by working with something called P5JS, is I'm going to show you how to actually take a code example, something that has HTML, CSS, and JavaScript, and host that with GitHub Pages, which will actually be quite simple, but I'm just going to put that in a separate video because it does involve programming and source code. But you can actually just with this video, put a text file or some basic HTML online. Okay, thanks for watching, and let me know what questions you have in the comments. Okay. All right, everybody. So that was my GitHub Pages tutorial. I think that was relatively short, at the most 20 minutes. Okay. So it's very hot in here. So I'm gonna have to wrap this up soon, because it's 2 o'clock already. I'm okay till 2:30. I want to see if I can do the superformula thing today. Let me just think about a P5JS sketch really quickly. I'm trying to think the best way to do it. Let's grab like, I'm trying to think of what would make the most sense to use. This was a fractal tree example I had from before. I don't know. For some reason, I don't feel like using them. Maybe reaction diffusion. These are all so slow. Running game. What's this one? Oh yeah. So let's use this one. This is my silly little platform game that you have to. And platform is the wrong term. So let me use this one. Okay. So I'm gonna that's called running game. And, okay, so, all right. Okay, everybody. There's some interesting comments in the chat. Okay, I'm going to really quickly just do a quick video of getting a P5 sketch hosted with GitHub Pages. Okay? Great. So I'm going to do that really quickly. Or do I already have pull requests on this? Let's see. Yes, somebody already has a pull request. I'm just going to merge this sight unseen. Let's just look here. I need a Git hug. Thank you. Okay, so I'm going to, I love this pull request. I'm going to merge it. Thank you very much. Great. Okay, so is this worth it? Because I think I'm gonna do this anyway. So I'm gonna do yeah. Okay. Okay, everybody, here we go. Let me cycle the cameras. Oh, I got like a little bit of a headache for a second here. All right, this is going to be quick, 5 minutes. Famous last words. Okay. This is a short tutorial to show you how to take a P5.js sketch and host it with GitHub Pages. So in order to follow this tutorial, it assumes two things. You have a GitHub account and you have a P5.js sketch. And the P5.js sketch I'm going to show you is this one, which is just a little simple game demonstration where there's an obstacle coming at you and you've got to hit the spacebar in time to jump over the obstacle. Okay, so you can see that's the basic sketch. Now, what is this sketch? It is a directory. In the directory, it's called running game, which is, I don't know why I called it that. And it has a set of files associated with it. It has an HTML file, 2 JavaScript files, and libraries files. The point of GitHub Pages, though, is you can host anything. You can make whatever. You can have as many CSS files, HTML files, as many JavaScript files. You can have directories, images, all that sort of stuff. But I'm going to take just this core basic directory and host it on GitHub using GitHub Pages. So the first thing that I need to do in my GitHub account under Rainbow Coder is I just need to make a new repository. I'm going to make a new repository. I'm going to call it P5.js sketch. Obviously, you should call it something better, but that'll work fine. Showing how to host P5.js sketch with GitHub Pages. I want it to be public, so people can see it. I'm going to initialize it with a README so it has something in it to start. And then I'm just going to hit create repository. Then I'm going to add a branch. This is key. I need to go under here, branch manager. I need to add a branch called gh-pages. I'm going to create that branch. Then what I want to do, just for safety reasons, I want to go to settings under branches, and I want to switch the default branch to gh-pages. I'm going through this a little bit quickly because you can watch my previous video where I do this in a bit more detail, but I'm going to show you the steps again here, but more quickly. So all I need to do is hit update. I want to say, I understand, update the default branch. I want the default branch always to be GitHub GH Pages. Only the stuff that's in that branch is viewable hosted online as a web page. So then the other thing I'm going to do just also for safety is I'm going to go back to my repository. I'm going to click here under branches. And I'm just going to, under master here, I'm going to click this trash icon all the way over on the right because I just want to delete the master branch. So there's no more master branch. This particular repository only has a gh-pages branch. So here we are. I have an empty repository with nothing in it, a gh-pages branch, and now I need to commit those files, my sketch, to the branch. Now, there's a bunch of different ways I could do it. I could clone this repository down, I could add the files, and I could push it back. But just for simplicity right now, I am going to just actually grab this whole directory and drag it in here. So GitHub Pages is GitHub as a tool allows me to upload files directly to it. And so it's uploading everything. And now I'm going to say uploading my P5.js sketch. And I'm going to say commit directly to the GH-pages branch. I'm going to hit commit, processing my files. It takes a minute, and there you go. Now, one thing you'll notice here is my files are in a directory called running game. I could have had them on the core directory, which I mean in the root directory, which probably would make some sense. Maybe I'll show you that in a second, but you can see that the files are there. So now where do I see the stuff? So the URL is always your username.github.io/your repository name. But if you don't want to remember that, you can always just click on settings and then scroll down, and you'll find here under GitHub Pages that it'll say your site is published here. So I can click here. Now the irony here is it's going to say it can't find anything. I'm getting a 404 error. That's because I actually have my index.html file in a directory called running game. So I've got to go add that directory right here, running game, and I'm going to hit, and I spelled it wrong. I'm going to hit running game, and now you should see there it is. So there's my sketch online, and I have a permanent URL to that sketch. So there it is, hosted on GitHub Pages. Now, if you wanted to just appear at the root directory, p5.js_sketch, what I would recommend doing is I'm going to go back to the repository. And actually, I'm going to clone it. I'm going to fix this by cloning it. So I'm going to go, sorry everyone, I'm going to go to this repository, Rainbow, where am I? P5JS Sketch. I'm going to grab the URL for cloning it. And I'm going to go here. And I'm going to CD back up to my desktop. I'm going to say git clone here. And I'm going to open that here. And I'm going to look at running game. So let's look at this. So, whoops, no. P5JS Sketch. So in P5JS Sketch, this is what's in that particular repository. And I'm just going to take those files, and I'm going to put them in the root directory. And then I'm going to delete that folder. And when I go back here, I can say cd into P5JS Sketch, and I can say git status. So you can see it's telling me I moved all these files around. I did all sorts of stuff. So I'm going to say add .-a to add everything and delete everything. And then I'm going to say git commit move files to root directory. And then I'm going to say git push origin. And now the really key thing, I want to put those changes back up. I don't want to say git push origin master. Remember, everything happens in GH-pages. So I'm going to push everything up, and I'm already authenticated. It might ask for your username and password. And now I should be able to go here, and you can see all of the files are now here just in the root directory. There's no more running game directory. And I can actually just now go to rainbowcoder.github.io/p5_sketch. You can see this is the URL that I'm going to. I can hit enter, and there is my sketch. So you can easily just have files in your GitHub repository as long as they're in the GH-pages branch. Then you know where to view those pages hosted on the web. So I showed you all the possibilities. I showed you uploading files just through the GitHub interface. I showed you cloning and making changes. But you can work entirely through the GitHub interface. You can work entirely locally through terminal. All of those possibilities are open to you. The only thing that you have to know to make sure is that all of your work is happening in GH-pages and that you know the URL, which is your username.github.io/the repository name. Incidentally, you can also have a custom URL that involves creating something called a CNAME file. I'll make another tutorial, which will be like part 9 at some point of this series of how to do that, or part 10 somewhere in this Git and GitHub tutorial series will be that video as well. Okay, so hopefully you found this helpful, and I will see you in some other part of the universe somehow, I hope. Okay. So, I don't know, what was that, 10 minutes? Maybe that was 10 minutes. I think it was pretty short, but it was definitely longer than 5 minutes. Okay, so that concludes that. Do I have the time? And it's 2:11. So let's see if we can do this super formula thing. I need to work on the math for this for a second. And I need to get set up. So I want to do this in P5. So let me get that running game sketch. So let me call this super formula. Oh, it's already taken, yeah. Underscore processing. I'm going to call this super formula. Really? Okay, hold on. Super formula. I thought oh, it doesn't, it's not giving me permission. I have too many accounts on this computer and the permissions are all screwed up. There we go. Now I can call this one super formula. I'm going to go in here, super formula 1. And put all this in here. And I'm going to open this with Atom. Oh, it's like a Git repository. That's fine. And I'm going to get rid of all the code. And I don't need this class. I'm going to delete this. Save, and I also want to run a local server now. move this over here. Oh, right. Okay, let me fix this. Sorry, I'm just doing some setup stuff, and I don't have the energy to talk through it just for a second. So I need to play my background music, but I don't have any background music. So coming soon, background music. Okay. We add setup and draw just to make sure things are working here. Create canvas. 400, 400 should be fine. Background 51. Okay, that looks good. This can move in a little bit. This can also move in a little bit. This can be minimized. Okay. Okay, so the other thing I want to look at now is superellipse. Let's start with this. Yeah. Okay, so I'm gonna I'm wearing a Pebble Time watch in case people were wondering. It's not an Apple Watch. Okay. Okay, so I need to discuss the math for this with you guys for a second because I'm not 100% sure about it. I don't think I'm gonna in this video tutorial derive everything. I'm just gonna kind of like talk through how it works. But I want to do this once. So here's a circle. A circle has a center point and it has a radius. And we know that if you were to make like a right triangle like this is like the x, this is a y, and this is like the radius of the circle, and this is an angle. We know a couple things. We know through Pythagorean theorem that x squared plus y squared equals r squared. And we also know that given r and theta, we can solve for x equals r times cosine of theta, and y equals r times sine of theta. Now, I've skipped a million things here. If this kind of math, this is something called polar coordinates, is not familiar to you, I would refer you to my polar coordinates and trigonometry video tutorial. But these are the basic formulas for dealing with a plain old circle. Oof. Sorry, it's very hot in here. I'm kind of running out of steam, but let me make this superellipse tutorial since I said I would do it. I just need to point the fan at me here. That'll help. Okay. Okay, so now the superellipse is written this way. So the circle is, in a way, all the points, a unit circle is all the points where A and B are 1 and n is 2. So that's the superellipse formula. Let me write that over here. Come on. Is x over x over a to the n power plus y over b to the n power. And these are the absolute value equals 1. So you can see this is that formula when what? When a and b are 1. When a and b are equal to r and n is equal to 2, right? Because let's say x divided by r squared plus y divided by r squared equals 1. This is the same as x squared plus y squared equals r squared, right? So this is a simple version of this formula. With this formula, we can also extract the equivalent of the polar to Cartesian coordinates saying x equals, and this is where I have to look this up. I'm just coming over here for a second. And I'm just going to leave that. I'm going to write it over here while I have that open. X equals, as a function of theta, equals cosine of theta to the 2 over absolute value to the 2 over n power times a times the sine of cosine of theta. Oops, and I ran out of space. OK, so we can sort of do the same thing with these formulas. So I think, and you can see sine of t is -1 if t is less than 0, is 0 if t is equal to 0, and is +1 if t is greater than 0. So I believe I could derive this formula, but I think I'm going to skip deriving the formula and just implement it. So this is the superellipse. Whew, boy, is it hot. OK, so if you guys don't mind, I'm also just going to take a 1-minute break to get some more water. So I'm going to just short 2-minute break. Whoops. Put this note up here. OK. OK, I'm very concerned with my note. OK, yeah, I'm going to go over what the sine function is. People are asking in the chat. OK, so I'm just muting my microphone, and I'll be back in 2 minutes. Okay, I think I'm back audio-wise. You guys can hear me okay? I'm trying to get some fresh air in this room. I turned the fan up higher. So you might be hearing some like audio in the background, but I will, I'm going to turn the fan down once I start this tutorial. I'm just going to wash the whiteboard. So the idea here, by the way, oops, here I am. So let me figure out what I am talking about. So first of all, I just want to fix one thing. Change this to say superellipse. So what I want to show you, what I want to open up first is so this is ultimately where this leads. We're kind of going to the point where you can do these kind of crazy 3D shapes, and maybe are you asking me if I feel unwell? Because I do feel a little bit ill, but I think I'm going to be okay for another 10 minutes. No, I got a little overheated, I think. I'm going to have to think about what to do about these hot days in New York in this room and get some different lights. But for right now, I'm actually just taking a break. I feel fine now and having a little water. So the idea here is kind of working up to doing these more complex 3D shapes, but with this particular formula and the same technique that I'm going to show you with, it's just an extension of this ellipse formula. See also superellipse, which I'm going to get from here. Okay, so I think I'm going to start with this particular visual reference. Okay, so this is going to be the last thing I'm going to do today. I think I'm just going to do the superellipse, and then I will reference the superformula, which I will do. I'll release the code for doing that, which is pretty similar, and then I will do a follow-up video on that next week. Okay, everybody. Super shapes. All right. Let's see if we can get, this is going to be 3 parts. Superellipse, super shape, 3D super shape. That's my goal. I'm definitely afraid of the 3D super shape, but we'll see if I can manage to get to that at some point. Okay. Super rainbow would be nice. Okay, I got to do this. Here we go. Last tutorial of today, and then I'm going to go outside into what will be cooler air. I'm going to turn this fan a little bit down, just so it doesn't mess the audio up. Okay, here we go. Here we go. And I guess I'm just going to start. I think I cycled the cameras. Let me do it again just in case. Okay. Hello and welcome to another coding challenge. This challenge is going to happen in 3 parts. The goal is to eventually, in processing, make these 3D super shapes. So there's like these weird, crazy formulas that you can find. This is my reference that there'll be a link to it in the video's description on paulbork.net, which goes through the math behind these super shapes and what they look like when you render them with different variables. But I'm going to start way back. I'm going to go way back into time into a much simpler place. And rather than make a 3D, so the last piece is 3D super shape. The second piece is 2D super shape. But the first piece is actually just something called the superellipse. The superellipse is going to be a simple example to show you how to build a shape that satisfies a particular formula. And that particular formula is right here, sorry, on Wikipedia. It is this particular formula right here. So let me talk to you a little bit about the origins of this superellipse formula. Okay, so you might be familiar. You might remember this shape from my previous video, polar coordinates and trigonometry. It is called a circle. So a circle is a shape that has a center point and a radius. And you can think of describing any point along the outside of that circle by that radius and some angle of rotation. But you can also think of it as, x and a y. And so we know through the Pythagorean theorem that with a right triangle, a squared plus b squared equals c squared, or x squared plus y squared equals r squared. We also know through the definition of what sine and cosine mean, sine being opposite over a hypotenuse, cosine being adjacent over hypotenuse, we can solve for x and y based on r and theta. So x equals r times cosine of theta, and y equals r times sine of theta. So knowing this, we can actually use these formulas to set a whole bunch of vertex points and draw a circle without the ellipse function, with begin shape, end shape, and vertex. Let's actually go do that really quickly right now in the code. And we're going to come back. So we're going to go do that, and then I'm going to come back to this formula and show you what happens to that particular ellipse. So if I go, I've got a blank code example right here. It's running in the browser. It's doing absolutely nothing. But I can, in draw, I can say, okay, let's make a loop. I'm going to say for var a equals 0, a is less than 2 pi, a plus equals some amount, like 0.1. I'm going to say, okay, I need to solve for x. And I want to have an r, a radius. R equals 100 or 200. 100 is fine. So x equals r times cosine of that angle, and y equals r times sine of that angle. So if I just draw a bunch of points at those x's and y's, and if I start also by translating, because I want the origin point, just for this example, to be in the center of the window, if I run this, and maybe I need to say stroke 255 so you can see those points, you can see there are all the points along a circle. For every, I'm incrementing an angle, and I've got all these points along the circle. Now I could connect them by saying here begin shape, and I could say end shape, and instead of point, I could say vertex. And then, now you can see I've got a circle, and it's actually even filled in. But just so you can see, I could say no fill. And you can see this. Now you notice there's a little break point here. It's because my last point doesn't actually equal my first point. And I could be more thoughtful about this, but I could also just say end shape close. So if I say end shape close there, then it's now closed. So there's the circle. So this is like, we're just easing into this. This is not a superellipse, it's an ellipse. And it's entirely based on this particular formula. Now, the superellipse formula looks a little bit different. It looks like this. X divided by a to the nth power plus y divided by b, and by the way, the absolute value of those, whether x is plus or minus, to the nth value equals 1. So you can see this is actually this is actually a particular case of this formula. What if a equals r and b equals r? I'm on the wrong side of this pen, or maybe I'm not. This pen's just getting worse. If a equals r and b equals r and n equals 2, what is this formula? This is x divided by r squared plus y divided by r squared equals 1, or x squared plus y squared equals r squared. And the absolute value doesn't matter because a negative or a positive is squared and it becomes a positive. So this formula is actually just a simple case of this formula. And in the same sense, this is a simplified, these are the ways to calculate the x and y based on theta for this particular formula. So a circle is actually all the x and y points that satisfy this equation. X squared plus y squared equals r squared. A superellipse, excuse me, I'm falling over here. I have superpowers of clumsiness. A superellipse is all of the x and y's that satisfy this particular formula. What if it's n to the 4th power? What if you have a different a and a different b? What kinds of shapes can you get if you plug different values in? So the question is, though, what are the equivalent polar to Cartesian transformation formulas? How do you get from theta all the different angles to the x and the y? That's how I did it code-wise over here, right? These two formulas were rather simple. How do I get the equivalent formulas for the more general superellipse shape? So I could try to derive it, but I'm just going to look up the answer for that on Wikipedia and implement that answer here in this particular code example. And perhaps if people are interested, I could do another video and we could try to look at a bit more behind the math or maths, depending on how you like to say it. Behind this. So let me go back to Wikipedia, and I can actually look right here. And you can see, by the way, you get different kinds of shapes based on what the value of n is. But this is really the formula that I care about. So what I care about is, how do I solve for x and y as a function of theta, function of the angle? And here I can see x as a function of theta is the absolute value of theta to the 2 over n power times a times some function called sine of cosine of theta. Okay, so let's at least see what happens. Can I copy paste this into my code? I can't even select it. So I'm going to try to remember this, and we'll go back and forth between it. So I'm now going to change this to be superellipse. So comment that out, and I'm going to go down here, and I'm going to say var x equals, I've already forgotten, the absolute value of cosine of that angle. And now I've got a little awkwardness because I've got these variables called a and b here, and I want to keep that. So I'm actually going to just change this to angle. I'm going to use the word angle here, just to be a bit more explicit there. So I want an absolute value of cosine of angle to, and I want to take that and put it to what? The absolute value of cosine to the 2 divided by nth power. So let's make a variable called na, which is going to be 2 divided by n. So to the na power. So x is, I know, the absolute value of cosine of the angle to the 2 over n's power times what? A times what? Some function called sgn, which I will make up myself. Sgn of cosine of that angle. So this, I don't have a lot of space here, so I'm going to move this out. So now you can see it. You can see this is me implementing that exact formula. The absolute value of cosine of the angle to the 2 over nth power times a times this function called sine of cosine of angle, which I'll get to. And now I need to do y is actually the same thing, but change this to sine, change this to b, and change this to sine. So, and this is y. So we need a few more variables here. Instead of r, I need a and b. So I'm going to make them both equal to 100 right now, and I need an n. And I'm going to make n, just for right now, equal to 2. So if n is equal to 2, this should actually get us just that original plain old circle. Right? Because what's 2 divided by 2 is 1 to the 1th power is just cosine of angle. So now how do we deal with this sine function? So the sine function is actually a special function that just says that you want the sine of whatever, any number that you pass in there. If that number is positive, I should get the value 1. If that number is negative, I should get the value -1. And if that value is 0, I should get the value 0. So the sine function is just a function that takes any value and tells you whether it's positive or negative. So we can actually write a function in P5 that does that for us. So back over here, if I write a function and call it SGN and it gets some value, all I have to do is say if value is greater than 0, return 1. Else, if value is less than 0, return -1. Else, return 0. So this is a sign function. It receives a value, and this is very long-winded. I'm sure you could come up with some clever, condensed shorthand way of writing this, but I'm being very explicit. Greater than 0, give me a 1. Less than 0, give me a -1, or else 0. This is actually going to kind of tell us what quadrant we're in that superellipse. So we should now, we have the formula in here. We should now, instead we're not using this simplified version anymore, we're using this formula now, we should be able to get a nice superellipse. So let me go back here, whoops, and hit refresh. I see the regular old circle. That's good. So let's get a little crazy, and let's put like the number 4 in here and see what I get. Ah, you can see now I have a rounded rectangle, kind of almost. So let's make a slider for n. So I'm going to create a slider. And I'm going to say slider equals create slider. When you make a slider, you need 4 arguments. What is the minimum value? What is the maximum value? What is the starting value? And what is the increment? And what I'm going to do is in draw, I'm going to say n equals slider.value. So now, whenever I tweak that slider, I should be able to change the ellipse. So that's n equals 2. And you can see as I move the slider, what I get. Ooh, now that was like really hard to see, but you can see as I move it. So I'm getting all the different possible superellipse shapes. Now I could also change A and B. Like for example, what if I make A 200 and B is 100? You can see that's just an ellipse now, and I get other kinds of shapes with that. So you can see this is the beginning of a super formula. It's just a superellipse. I have a single angle. I have some weird sort of conversion that I need to do to get an x and y, and then I have a begin shape and end shape. So in the next video, what I'm going to do is instead of showing you how to do this with just, and let me come back, how to do this with just this particular formula, the next formula I want to approach is how do I get all the x and y's that satisfy, I'm going to scroll up to this particular formula. So when I use this particular formula, which just has a lot more math in it, but essentially the code's going to be exactly the same, you're going to see how you can get all the variety of these different kinds of shapes. And then at some point, once we get to there, we should be able to then take this formula and move it into 3D to create volumes. So I actually have never done this part before. I've done the superellipse and the 2D super shape, and that'll come in the next video, which I'll release at some point from now, and then we'll move into 3D. So I hope you enjoyed watching this superellipse video. Give it a try. Try adding some colors in it. Can you make a super rainbow? I don't know what that would be. Try making that and see what you get. What other kind of interactive features can you do? What kind of questions do you have about the math? And let me know how that goes. Thanks for watching. Okay. So somebody is pointing out in the chat that JavaScript has a math.sign function. So I could have just used that. And I wonder if P5 actually has that function. Let's try replacing it. Math.sign. Oh yeah. Looks like I could just use that. So I should have just used that. I don't think that's overloaded in P5 in global scope. Yeah, so it's not. But, you know, we learned something. So that's a good, yeah, the formulas are scary. The point of these videos is to try to make them seem less scary. I don't know if I succeeded at that. Okay, everybody, so it is about 2:40. I'm about 10 minutes past when I said I needed to go, but I can tolerate a few more minutes here. If anybody, I know that some people requested like some question and answers. If anybody has any questions they want to ask, I can answer maybe just a few general random questions before I go. I'm looking in the chat to see if anybody made any other good points that I missed. Oh yeah, so I should, one thing, I'll mention this when I do a follow-up, I should really be more thoughtful about here. Like, so I probably should create a variable called like step and say like 2 pi divided by 100, just so it's like there's sort of an even number of points for all the angles from 0 to 2 pi. But in the end, it kind of looks the same. But yes, that's going to matter more when there's a bit more of a finer detail in certain things. So I'm going to leave that out, though, because I'll try to remember to mention that in the next video. Let me see what other questions there are. So yeah, so the funny thing is, everyone's asking if I have feet. So first of all, I do have feet. I don't know if there's any like non-awkward way I can show you my legs, but whoa, okay, I'm almost knocked over the table there. Everything's fine though. I just bumped. But I actually, what's funny is I have these rainbow socks. I was thinking, oh, I could wear the rainbow socks, but nobody will be able to see them. I need a rainbow T-shirt, I guess. Okay. Are your polar coordinates and trig tutorials on YouTube? Yes, they are. So let me find those for you. Let me just Google, actually, so let me go to YouTube/Schiffman. And the place that you could find them is under here. I don't know how well you can see this. The Nature of Code videos. And I'm pretty sure most of them are in this Chapter 3 oscillation playlist. So trigonometry and polar coordinates here. This I should warn you about, some of these videos are really old, being like I made them like 4 years ago. Quality isn't as good. I think I was funnier then. I was a little bit crazier. So let me know how that goes, if that matches up well. But this is the one, and obviously there's other aspects of this because this is going towards like simulating pendulums and springs and that sort of thing as well. Are you ending soon? Yes, I'm going to go in just a few minutes. This has been a 2 hour and 15-minute live stream. 2 hours is really my limit. I need to do a better job of keeping myself to that. I also asked, are you a teacher? So I teach at a program. It's called ITP. I'm just going to go to the website. It's at NYU. This is the URL, tisch.nyu.edu/ITP. It's a 2-year master's program in technology, art, and creative applications of technology, loosely. I encourage you to learn about this program. And I also do have an online course, which is with a company called Cadenze. And this is the URL for that, cadenze.com, courses/the nature of code/info. So this is something you can sign up and take online as well. What temperature is it? Well, let me look at the weather in New York City. And I would say it's probably like 5 to 10 degrees warmer in this room. It is 82 degrees, sunny and 82 in New York City right now. I would say it's probably 90 degrees in this room. So everyone's, I'm getting, a lot of people have been asking about 3D reaction diffusion. So to be honest, okay, so the reaction diffusion example tutorial works on, so I'll mention this, I'll try to get people started on this. So the reaction diffusion tutorial works by having a particular amount of chemicals of A and B in a particular cell in a two-dimensional plane. And it involves having weights, 0.2, 0.05, 0.05, 0.2, 0.05, 0.2, 0.05, 0.2, -1. So it involves using a formula to add up all of the chemical amounts of the chemicals of this cell and its neighbors. If you watch the video, you'll see that formula. So to do that in 3D, what you'll need to do is not only consider 2D neighbors, which there's only 8 of them, but in 3D there would be 9 plus 9 plus those 8. So there's 27 cells total. So you'll need to, and actually if you look at my Menger sponge video, I do a sort of 3D cube thing with 27 cells, which you can look at that as some clues. So it's just about taking that formula and that instead of having a nested loop through 2 rows and columns, you need a 3 nested loop through rows, columns, and depth, I guess. And once you've done that, you also need a way of visualizing it. So one way of doing it might be to have each cell be a cube with transparency and have the level of transparency tied to the amount of chemicals. I'm not sure. So there's a variety of ways you could try approaching that. So I honestly haven't done that before. I really try to stay away from 3D stuff, but I would encourage you guys to get started on that, and I'm absolutely happy to try doing a video at some point. Oh yeah, everybody really wants to do, I've made a bunch of videos about Perlin noise already. So if you, I'm curious what would come up, but if you Google Perlin noise Schiffman YouTube, you can see there's several videos. 3D terrain with Perlin noise. There's some other people's Perlin noise. There's this Perlin noise video. There's a Cadenze video on Perlin noise. So you should be able to find that. Yes, reaction diffusion is an example of a cellular automaton. Works exactly the same way, in my view. I know everyone really wants me to do videos on sound. I gotta bump that up. So that'll happen. Let me commit to doing that maybe next week. I want you guys to keep me honest about that, especially in the Slack. The Slack is where I'm kind of have a discussion. The Slack is a group you can join if you subscribe to the Patreon, and I have a topics discussion group going on in there. So, but just tweet me, remind me in the comments, that sort of thing. A harmonograph. I don't even know what that is, but I'm going to look like that. So I'm definitely going to do sound. I apologize for not getting to it. Honestly, the stumbling block is I got to set up a mixing board in here and get sound coming out through the stream. And so I need to do that. And I'm sort of motivated to do that. I just haven't gotten around to it. Because a lot of times what happens here is I come here and rather than work on my setup or topic ideas, I just turn on the recording. But if I do another live stream this week, it would be Thursday or Friday. Otherwise, the next one will be next Monday or Tuesday. So, okay, so let me briefly just mention now that I'm kind of wrapping up. If you want to subscribe to updates, email updates for when I'm going to do these live streams, you can just go to schiffman.net, and there's a little place where you can put in your email. If you're interested in supporting this channel through Patreon, and I hesitate to plug this too much because I'm thrilled for people to watch and enjoy and participate in the community, but you can support it through Patreon at patreon.com/codingrainbow, and the benefits that I'm offering for that are a private Slack channel, something else that I can't remember, and a shared Google Drive where you can sort of download all the video files if you want to watch them offline. Honestly, if somebody really wants that stuff and doesn't want to subscribe to the Patreon, I probably would say okay. But I guess I have to have some stuff. Anyway, okay. Okay, so, so I'm going to use P5GS for sound. So I'm going to do all my sound stuff in the browser using P5GS. I will do sound effects, sound synthesis, and even analyzing sound from a microphone. So I'm going to do all that type of stuff in P5GS. Okay, so I think I'm going to go. I'm going to try to find some cooler air. Thank you guys for being patient with me today and watching and participating and being enthusiastic and supportive. I really appreciate it. I feel like some of these math topics are kind of difficult, and actually, to be honest with you, I would be so pleased to do the sound video tutorials because I feel like those will actually be a lot simpler in many ways to do. And hopefully we'll have cooler. I don't know what the weather's going to be in New York next week. New York weather. 10-day forecast. Let's see, when are there, how do I get the 10? Tuesday, Wednesday, Thursday, Friday, Monday. It looks like it's still going to be warm, but hopefully we'll get some cooler days, so I'll get some cooler air in here and figure out to make it less hot. But also I think if I do 1 hour, take a break 1 hour, it won't heat up as much. So anyway, okay, so thank you guys for your support. I'm going to turn off the stream. I still have many more. There will be more videos that will get uploaded as standalone chunks. I think one thing I'll say that I'm pleased with is I've actually had enough people now watching my YouTube channel that I honestly can't keep up with the comments. So I was daily making sure I responded to every single comment on every single YouTube video for a while, and it's not that it's exploded, but I will try to go back and answer as many of those that I can, and you can also contact me on Twitter @Schiffman as well with feedback and suggestions. Okay, I'm going to hit a button over here, which is going to turn off this stream, and I'm going to say goodbye, and I look forward to seeing you guys in the next live stream. I'm 100% committed to do these at least once per week, and if I can, I'm going to do them twice a week. So right now, it's up in the air whether I'll get one in on Friday, but so it'll either be on Friday or next Monday or Tuesday. Okay, see you guys soon. Thanks for watching.